So I was playing Call of Duty Black Ops 2 earlier today and noticed a structure in the map Nuketown that is statically indeterminate.
For those who don't know, a statically indeterminate structure is a figure which contains more unknown forces than can be solved for by using equilibrium equations alone.
The structure I found was a bed in one of the houses. The bed is attached to the wall by a hinge and to the ceiling by 4 prismatic bars.
Therefore, the forces acting on the bed are the tensions in each of the bars and the reaction forces in the hinge.
Let's say that someone is also sniping out the window from the end of the bed opposite the hinge. Their weight would also be acting on the bed.
So what we want to know are the tensions in each of the bars as well as the reaction forces of the hinge.
Before we start, there's some information that we know or may assume. We can assume that the weight of the sniper is roughly 180 pounds and the bars are 3 feet long, half a foot wide, and made of aluminum.
We can also assume that the bed is 7 foot long, 3 foot wide, and a half foot thick and made out of steel. We will also neglect the weight of the bed and the weight of the bars.
Also noted is that 2 of the bars are located half a foot in front of the hinge, while the other 2 bars are located 7 feet in front of the hinge. So as you can see, this is a 3D rendering of our bed with 2 of the bars half a foot in front of the hinge, which is H, and the other 2 bars 7 feet from the hinge, which is TA, and then as well the sniper, which is also 7 feet away from the hinge.
You can also see that from our two-dimensional free body diagram. We can use this hinge point here as our x-axis, and then from here we have our y. So we have our positive x going this way, and our negative and our positive y going upwards.
Now we move on to our equilibrium equations. Summing the forces in the x direction, it just comes out to be the reaction of the hinge in the x direction equals 0, since that is the only force in the x direction.
Next we have the sum of forces in the y direction. We start with our reaction at the hinge, that is there, and then we have our 2 tensions at A, and then we have our 2 tensions at B, and we have to subtract the weight of the sniper.
And then we move on to the moment equation. Since two of the bars are half a foot from the hinge, in the negative x direction, it's negative a half times 2TB. Then the other 2 bars are 7 feet from the hinge in the negative x direction, which is 7 feet times 2TA. And then the weight of the sniper is also 7 feet from the hinge, but its force is in the negative direction, which produces a positive moment. So it's 7 feet times W, and that all has to sum to equal 0. As you can see, 7W equals tension in B plus 14 times the tension in A. Now it's time to move on to force displacement. As you can see, the displacement of the bars with a tension of TA equals the tension TA times the length of each bar over the modulus of elasticity for aluminum times its cross-sectional area. Much the same, the displacement of B equals the tension of B times the length over the modulus of elasticity for aluminum times its cross-sectional area.
Okay, now we move on to our compatibility equation, and since we found our 2 elongations for bars A and bars B, and we know that this won't bend, we can come down here and we can say that the elongation of A and the elongation of B are both proportional to their lengths. So the elongation of A is over 7 foot, and then we'll have our elongation of B at a half a foot, and those 2 together, they have the same ratio. So we end up getting that the elongation of A equals 14 times the elongation of B. Now that we have our 2 elongations, we can plug in our force displacement equations into our compatibility equation. And doing that, we get the tension of A equals 14 times the tension of B.
Then we will plug our equation that we just got, which is equation 7, back into equation 3, which is our moment equation. There. In doing that, we can solve for the tension in B, which comes out to be 6.39 pounds.
Now plugging the tension of B back into our equation 7 up here, we can find that the tension of A is 89.54 pounds.
We can then plug our values for the tension in B and A into equation 2, which is our force in the y direction equation, and we can get the value of the reaction of the hinge in the y direction, and that comes out to be negative 11.88 pounds. Thus we have all our reaction forces for the hinge as well as all of our tension forces.